acronym IMF for intermolecular forces. Now they sound very similar, inter versus intramolecular. Here's a great picture showing you kind of the difference between the two. On the left, we have an intermolecular force, and on the right, we have an intramolecular force. The prefix inter really just means between. Think like an interstate. An interstate goes between states. So in this case, an intermolecular force goes between different molecules. So notice I have a nitrogen molecule here and a nitrogen molecule there. The attraction that's occurring between those molecules is intermolecular. Within the molecule, the prefix intra means within. So an intramolecular force is within the singular molecule. So this right here would be an intramolecular force. Now, really, we can talk about inter and intramolecular forces, and really we've talked about one of these already. The one that we've talked about is an intramolecular force, or the attraction within a molecule. And remember, we can get pretty specific. So if I look at this example here, the intramolecular force happening within nitrogen is one, it's a covalent bond. Why? Well, it's because it's two nonmetals sharing their electrons. Now, if you remember in the previous video, we can actually go a step further and not just say that it's a covalent bond, but we could say, is it polar covalent or is it nonpolar covalent? Well, if we look here, these nitrogen atoms, neither one is stronger than the other. In other words, neither one is more electronegative than the other. So there is no dipole, meaning they're sharing those electrons equally. And remember, if they share those electrons equally, we would say that this is a non-polar, right? Because they're sharing them equally, covalent bond. And remember, that is an intramolecular force. Now, different intramolecular forces, what it really deals with is ionic, covalent, and metallic. Ionic, covalent, and metallic. Okay, but remember with covalent in particular, we can break this into polar and nonpolar, similar what we did in right before we talked about this, right? So the intramolecular forces we've talked about. This, in this example here, this is a nonpolar covalent bond. What we haven't talked about are these intermolecular forces, or the force of attraction between molecules. Because remember, right, in this room right now, in the room where you're at, wherever, there is roughly 78% nitrogen. So with that said, there's millions, billions of nitrogen molecules that are all interacting, not only within or intramolecular, but between each of those, and here's just a small snapshot, but interacting between them, right, or intermolecular. So what we're focusing more so in this video is on the IMF, or the intermolecular force. Now, a couple things, now that we understand the difference between the two, is IMFs are really responsible for really like phase changes and boiling points and melting points. So when you have a stronger intermolecular force, it's harder to break. It's a stronger attraction. Think of it as if I'm holding on to somebody with my pinky, or I'm holding on to somebody with a firm handshake. The stronger I'm holding on to something, the harder it is to break. So these are going to have higher boiling points and melting points, which is what this says. So maybe rather than a weaker intermolecular force might, say, boil at 70 degrees Celsius, a stronger intermolecular force might boil at 100 degrees Celsius. And because of this, and you'll learn more about this in thermodynamics, this leads to a larger enthalpy of vaporization and fusion, which really just means the energy that it takes for a molecule to break those intermolecular forces to undergo a phase change, go from a solid to a liquid, or liquid to a gas, or vice versa. So strength of intermolecular forces is important because we see these different effects as a result of it. We can also have greater surface tension the stronger the intermolecular forces are. So we'll talk about this a little bit later on, but surface tension is really just a measure of how well does that liquid hold itself together. The stronger those intermolecular forces, the more attracted to each other they are, the harder it is to break, and it's going to take more energy to break that surface tension. I'll give you more examples here shortly. This right here is a good kind of overall picture of strength. So if we're talking intramolecular, which remember is your metallic, your covalent, and your ionic, generally speaking, metallic is usually kind of weak, and there's a little bit of an asterisk there. Now keep in mind, and really what we like to focus on is covalent versus ionic. Remember, ionic is really strong because those electrons have now transferred from each other, whereas covalent, they're being shared. Non-polar covalent isn't generally quite as strong as polar covalent. But again, that's just kind of a general strength, kind of high-level overview of what that looks like. Where I want to focus more is on intermolecular forces. We're going to look at each one of these in this video, and hopefully by the end you're able to identify what the intermolecular force is and how its strength generally compares. So the first one is called LDFs. These are called London dispersion forces or van der Waals forces. They're generally pretty weak. And then we move into dipole-dipole forces, which are stronger than LDFs, but not crazy strong. Then we have hydrogen bonds, and then we have ion dipoles. Now, hydrogen bonds and ion dipoles are very strong in terms of intermolecular forces. Now, let me be very clear. Generally speaking, intermolecular forces are much weaker than intramolecular forces. But when we're looking at solely intermolecular forces, hydrogen bonds and ion dipole are generally very strong. There's some overlap because a lot of people might not consider an ion dipole force technically as intermolecular, but I just wanted to include that there. The big three are generally LDF, London dispersion forces, dipole-dipole, and hydrogen bonds. So let's look at LDFs, or London dispersion forces, first. So London dispersion forces are also called van der Waals forces, and these are very, very, very weak. Okay. One other thing to note is that all molecules have LDFs, or have London dispersion forces. Now, how you're going to differentiate between an LDF and a dipole-dipole, and I tell my students this all the time. If you're confused right now, give it just a few more minutes until we get into dipole-dipole, and you'll kind of see the similarities and differences. The biggest thing between an LDF and dipole-dipole is the dipole, which remember is the unequal sharing of electrons, is temporary. So for example, I've got some pictures here. Let me kind of explain them to you. I've got two chlorines bonded together. Okay, now if I look at the Lewis structure of chlorine, chlorine's Lewis structure looks like this. Now what you'll see is neither chlorine is more or stronger or more electronegative than the other chlorine, right? Which means there is no dipole here. Which means that technically speaking, this is a non-polar bond and molecule. Okay? Now, where this kind of differs, and before I move on, let me talk about this. This is this picture, where those chlorines, they have the same really electronegativity, and those electrons right there are being shared equally. So it kind of looks like this. Now, what we have to keep in mind is those two electrons being shared are moving so rapidly back and forth, where if I freeze time for a split second, this is how I like to describe this, okay? So they're moving back and forth really fast, but if I freeze, what we'll find is that those electrons have now shifted to one chlorine.